Video 4 of the master course on quantum chemistry of molecular electromagnetic properties. The topic of this lecture is the Born-Oppenheimer approximation. The masses of the nuclei in a molecule are at least a factor of 2000 or 3 orders of magnitude larger than the mass of an electron. The nuclei are therefore much slower than electrons. And we can therefore assume that electrons will instantaneously adjust to any change in the position of the nuclei, and that we therefore can find a wave function for the electrons for each arrangement of the nuclei. Let us therefore partition the total molecular Hamiltonian operator, which we had written up in the last lecture, in two parts. One part, which is the kinetic energy operator for all the nuclei in the molecule, and then the rest, which we then can call the molecular field-free electronic Hamiltonian for fixed positions of the nuclei, where we have still the kinetic energy of the electrons, the electron-nuclear Coulomb attraction, the electron-electron repulsion, and we also add, although it does not really belong to the electronic Hamiltonian, we also add the constant term for the nuclear-nuclear repulsion, so the repulsion between the nuclear charges. And this, for fixed nuclear coordinates, this is just a constant. But adding this to the Hamiltonian has the nice consequence that then the energies obtained from this Hamiltonian are actually the total energy of a molecule for fixed nuclear coordinates. As a next step, we want now to write up an eigenvalue equation for this operator, which I have given here. And of course, you could call that a time-independent, field-free electronic Schrödinger equation for a given set of nuclear coordinates. But essentially, it's just the eigenvalue equation for these Hamiltonians, where we here get some energies as the eigenvalues of this Hamiltonian, and we have a wave function, which is then the eigenfunction of this Hamiltonian. Now, since this Hamiltonian is for one particular set of nuclear coordinates, meaning for one geometry of a molecule with a particular bond lengths and bond angles, then of course the energy is going to depend on these positions, and also the wave function changes when we change the nuclear coordinates. The wave function itself is just a function of the positions of the electrons, but because of the Hamiltonian dependence on the nuclear coordinates, which means the Hamiltonian changes when we change the nuclear coordinates, we get a different equation, and therefore we will get a different value for the energy, and we get a different wave function, which is still just a function of the electronic coordinates, but it's a different function. And this dependence, which is here also indicated by this semicolon, is called, it's a parametric dependence. So the wave function, the electronic wave function, depends parametrically on the nuclear coordinates. But this wave function here is just what we call the electronic wave function. Now the total time-independent wave function of our system is in the Born-Oppenheimer approximation, now approximated by a product wave function. A product of one of these electronic wave functions and a nuclear wave function, which we have not yet determined how it looks like. So we write it up as one simple product function, where we have the electronic wave function, which is a function of the electronic coordinates, and as I said before, depends parametrically on the nuclear positions. And then we have this nuclear wave function, which of course the variables are then the nuclear coordinates. Now we're going to insert this product ansatz for a wave function in our time-independent Schrödinger equation with the full Hamiltonian, meaning the Hamiltonian, including also the nuclear kinetic energy term of this, what we call the electronic Schrödinger equation. And then we will try to do, as always, separation of variables. But we will soon find out that this is actually not possible if we do not neglect two small terms. And which terms that are, you will find out in one of the exercises. But if we neglect those two small terms and we make use of, then we can derive an equation for the nuclear wave function, which we'll call the nuclear Schrödinger equation. This is a function where we have the nuclear kinetic energy operator and what we call the electronic energy appears. So the electronic energy here takes over the role as the potential for the motion of the nuclei. The eigenvalues of this nuclear Schrödinger equation are actually the total energies of our molecule. So it's not only the nuclear energies, but also plus the electronic energy. So this is the total energy, and here we have the electronic energy. Now, as I said, the total electronic energy takes over the role as the potential for the motion of the nuclei. And it's a function of the positions of all the nuclei, so it's a hypersurface. And therefore, the total electronic energy is often also called the potential energy surface. In the following chapters, we will only consider the electronic wave function. Only in a much later chapter, we will return to the nuclear Schrödinger equation. And therefore, in the next following chapters, we will drop this dependence on the parametrically dependence of the electronic energy and the electronic wave function on the nuclear coordinates in order to make the equations less cluttered.